my website and you go to Publications, Books, you can download the MATLAB figures. If anybody had all the MATLAB codes, each one generates by its name. The name of the code, it corresponds to a figure in the book. So I will share with you also the material, but here in the example that I showed before, figures 2 to 5, these are figures 2 to 5. You see, this is figure 2, 3, 4, 5. These figures, they correspond to figures 2.2 to 2.5. So when you download these zip files, you open figure 2.2, the MATLAB code for figure 2.2, you will get this figure. Okay, and so on. So you can open the code, you can look at it, you can change parameters, and so on. So you're supposed to return the assignment tomorrow. If you need more time, it's okay, you know, no rush. If another day, it's also okay, okay? But try to do it because it will help you to understand the material. And also, a good thing, with at least with the MATLAB assignments, each one can work alone to think about, play with parameters, change parameters, so on, and then try to jointly with other people to discuss, because everybody will do something else. Discuss what you did, what the other one, what he did, he or she, why are the results like this. You can make changes and try to discuss with each other, okay? This is helpful. Any questions or any problems with the assignments? Any questions? Okay. So yesterday we talked regarding the quiz. There will be some questions. It's not closed. It's like a close. You just need to choose answer from a few options. It will be just based on understanding. So you don't need to open the material. Without any material, just to understand. It will not include derivations that you need to find mathematically. It's just to see the understanding. It's more actually for us to see the understanding in the course. Okay, so if you read the slides, you understand what I talked yesterday and today. It should be easy. Okay. Yesterday I talked about Wiener filter. Okay, so do we have here one? So single channel signal enhancement using Wiener filter. Oh, one is enough. Okay, thank you. So the problem was that we have some measurement, a signal, yt. T is discrete. And we know that our model contains a signal, desired signal, plus noise. And we know that the signal and the noise are uncorrelated. We can say even statistically independent, but for us here, for the Wiener filter, it's enough that they are uncorrelated. And then we wanted to find an estimate of the sample. Zt is an estimate of the sample on time t using L samples, L past samples of y. So we obtain it as H transform y. And y is a vector that contains L past samples of these signals. So this is a causal estimation. And we talked about differences between estimation, prediction, causal, non-causal, and so on. So for Wiener filter, if we want to find the filter here, we need to find the mean squared error, which means that if we take zt minus xt, and we take, this is the error, and we take the squared error, and we take the mean of this squared error. So we call that JH, which is the mean squared error. And in order to find an optimal filter, an optimal Wiener filter, we need to express this mean squared error as a function of h. This is what we did. And then we found h that minimizes over all h. Okay, so if I need more space here, okay, so we minimize these JH, the mean squared error, over all possible h. And the filter that finds this minimum, we call it H Wiener. And if we use this filter, the Wiener filter, so JH Wiener, this is the minimum mean squared error, the minimum mean squared error that can be achieved for this problem. And we saw different expressions for the Wiener filter based on information. And the information that we need is actually the correlation matrices, Rx and Rv. And we talked that these matrices are the size L by L samples. So we have L by L samples. And it actually contains that the correlation between any samples inside the vector x. So if we take vector x of L samples, we know the correlation, the average. Okay, so it's a correlation between any two samples. And this information is very important, and it's not easy to get in practice. So there are different methods. Okay, any questions on that? Now, let's continue. So we saw that we can write the mean squared error as a superposition of two terms. First term, we call it JD, which is relevant. It comes from the distortion of the signal, plus J, we can call it residual noise or something like that. We call it N, it can Rn or whatever. It doesn't really matter, but these two terms, we can either try to minimize their summation, or we can try to do different things. Okay? So this comes from the residual noise. Why? Because if we write this, so we can write it as the expectation of Z, which is H transpose X plus H transpose V minus XT. So you see that we have two terms here. We can write it as, let's write it over here, expectation of H transpose X minus XT plus expectation of H transpose V. Okay. So what we try to achieve with the Wiener filter is actually to minimize the sum of these two components. But sometimes we want to have undistorted signal. Maybe we want to put more emphasis to this part because the distortion is more important. Maybe we want to give more emphasis on this part. So we want to reduce more noise. So we have a trade-off. We have a trade-off how much noise we reduce. What is this part? And what is this part? So instead of minimizing this sum, the mean squared error, we can try to minimize summation like this. And we will call it, for example, J mu H. Okay, so we have a parameter mu. Now, mu is larger than 0. Positive number. So if mu, this parameter, is larger than 1, it means that we give more emphasis to this part compared to this part. So if mu is larger than 1, it means that we want to reduce, this part is more important because we put here a more weight. So what will happen if we found here, if we find H, let's call it H mu, okay? And we can say H mu trade-off. We can call it something like that. This is the trade-off parameter with a parameter mu. And this will be the filter that minimizes over H, J mu H. So we know that for mu equals to 1, H, we can put the T. This will be the trade-off. Let's say that just a notation. So we call it trade-off with a parameter mu. So actually, it doesn't really matter how you denote things, but this will be the trade-off filter with a parameter mu. So for mu equals to 1, it will be equal, so if I put here 1, it will be equal to the Wiener filter, of course. But if I take mu larger than 1, what will happen? This filter will result in more noise reduction because we give more weight to this part. So it will result in higher noise reduction because we want, if this is large, so we want to make this smaller by making this smaller, even further compared to the Wiener. So it will come on the account of this part. This part will be larger. So mu larger than 1 will result more noise reduction, but also more distortion. Okay? So let's say that Jn H T mu will go, if this is large, it has to go down but at the expense that JD HT mu will go up when we try to minimize this. And vice versa, if mu is smaller than 1, we will get, if it's smaller than 1, so we put less emphasis. This part is less important, so Jn will increase, which means that this filter will reduce less noise. So if we reduce less noise, if we take mu smaller than 1, means that this part is less important, so there is more importance, relative importance to this part. So JD, the distortion, you see this is the distortion, will, the mean squared error for the distortion, it will go down. That's why we call it a trade-off filter. So you see that this parameter, actually, we can interpret that parameter as a Lagrange multiplier. Because this mu can be regarded as a solution to an optimization problem like this. So we can write the optimization problem like this. Suppose that we want to minimize JDH subject to NH equals to some value. Okay, so we can say JNH, I deleted that, but it's, suppose that I give here a certain value. Let's say Aleph sigma V squared, for example, or something else, whatever. Okay, but suppose that I want to restrict this value to a certain value, which means that how much noise I want to suppress. So I limit that, how much noise I want to suppress, and then subject to such a constraint, I would like to minimize this. So this will be using a Lagrange multiplier. I can use a Lagrange multiplier mu, and it will be equivalent to this problem. But here I can change mu such that the constraint is satisfied. But if I don't care about this constraint, I can choose any value of mu. If I want that this will be equivalent to this problem, I need to change mu until some constraint is satisfied. This is the only difference. Okay, so let's see it here. So this is the trade-off filter, and it's very important in practice to have some trade-off between noise reduction and distortion. Okay, because the Wiener filter, it tries to minimize the total mean squared error, which sometimes we don't want that. We want to control how much distortion and how much noise reduction, because it's a kind of trade-off. And sometimes it's subjective. For some people, they want less distortion. Some people, they want more noise reduction because they don't want to noise. But this is a trade-off. And in some devices, you can also change the amount of noise reduction. And if you try to reduce more noise, you know that it results in higher distortion generally. Okay? So it comes at a cost. So we can define this problem, something like this, okay? Minimizing the distortion based mean squared error subject to some constraint. And then using Lagrange multiplier, we can write it like this. You see, this is, we can remove this part because it's constant. This is independent of h, so we can remove this. And then we try to minimize. We see what is the trade-off filter, what is this vector that minimizes this sum, where mu is any parameter that is larger than 0. And we now understand also what is the effect of taking mu larger than 1 or mu smaller than 1. If mu is 1, then we get the Wiener filter. But if this is our objective, to get Jn, which is the noise reduction or the noise, residual noise based mean squared error, then we need to find, maybe numerically, maybe by explicit expression, it doesn't really matter. But then we need to find the exact mu that such that this constraint or requirement will be satisfied. Okay, very simple. So what do you think? How the solution to this problem looks like? If I go here, what will be the solution? What do I need to do? So I take derivative of this with respect to h and equate it to 0, just like what we did for the Wiener filter. Actually, you can take the Wiener filter and instead of putting instead of having Jn, we will get mu multiplied with this part. So actually it's just like multiplying RV. If we multiply RV with mu, we get the trade-off instead of the Wiener. Okay? But don't try to guess. This is more intuitive. Yeah, it makes sense that if you multiply RV with mu, then you give more emphasis to this part. And actually, if we find if we have exactly the expression for J, and we put mu, you will see that here we have mu H transpose RV H. So when we put mu, it's just like applying RV. It's the same. Okay? Do you see that? Maybe I will write it. I don't want to go to the solution yet, but let me go back to the expression of JD and JN. Okay? Even though it's very easy to find it here, let's do it here instead of going to the slides. I want you to be familiar. We said that Jn, we call it Jn, okay? JNH is the means expectation of H transpose V squared, right? So this is expectation of H transpose V, V transpose H. It's the same, but it's more convenient to write it this way because this is a scalar. So I write this scalar differently. One here, one here. But it's the same scalar because the scalar transpose is the same. But here I can put the expectation into the inner side. So I get H transpose RV H. So if I multiply this with mu, it's the same as multiplying RV with mu. And then we get the same solution of the Wiener filter. So you don't need to do the derivative and equate it to 0 again. If you, of course you can do that, But if you know the solution for the Wiener filter, you know immediately the solution for the trade-off filter. You just multiply RV with mu, and you get the solution. That's why you see that the solution becomes like this. You see, it's the same solution as the Wiener filter, but we replace, instead of RV, we put mu RV. And by the way, all the expressions that we saw before, okay? So you just, instead of RV, you put mu RV, okay? But you need to be careful, because if you have another expression, like here, in this expression, this is the solution. But if you change mu equals, if you take a different expression, for example, if you take Rx now, and instead of Rx, you will replace it with Ry minus Rv. You don't multiply Rv with mu, because it's not true. So you need only to take the solution. Okay, so we can get different expressions and so on. Now, we can keep this filter with the parameter mu and take mu larger than 1, 1, or smaller than 1. And we know what does mu, how does it influence the mean squared error, or the solution and noise reduction, the trade-off between noise reduction and distortion. Alternatively, we can change mu such that the constraint here, the constraint will be satisfied, which is the same as the noise reduction factor. Noise reduction factor is equal to 1 over aleph. Okay? So we can choose mu such that this constraint will be satisfied. Okay, so it's up to you. I would like to go to an example, but before I go to an example, any questions so far? Okay, so I will go and show an example. But before that, you have this, what we talked before. And also we have this property. Remember that we talked about that the Wiener filter, with the Wiener filter, the output SNR is always larger than the input SNR, even though we didn't talk about SNR. So this is true for any parameter mu which is larger than 0. With any trade-off filter, the output SNR will be always larger or equal to the input SNR, which is also something nice to have. Because we didn't work, we just worked about minimizing. By the way, it depends on the model, okay? So for this model that y equals to x plus v, and obtaining the trade-off filter, we have this result. But it's not so obvious, okay? You need to check and prove it. So the proof is here, okay? So you have here the proof. But it's nice to know that the output SNR is increasing, even for any trade-off filter with any parameter mu. Now let's talk about an example. An example, it will make things even clearer. Suppose that we have a signal, x, and we don't know too much information about the signal. We just know what is the correlation between any two samples of x. So the correlation between two samples of x goes or decays by this distance. And alpha can be any number between 1 and -1. Okay, so we have the correlation. So if the distance between the samples is large, we see that the correlation can be, it will become smaller. And also we see that alpha can be negative. What does it mean, negative? If alpha is negative, what does it mean that the correlation between two samples is negative? So yes, so it changed sign. So correlation can be with the same sign or change the sign. It means that if two samples have similar values, so if we know one, we know that the other one is close to that. Or it's in the other sign, so it will be negative. By the way, if alpha, question, if alpha is 1, okay. Okay, so it means that the two samples, if you know one sample and the correlation is 1, okay, so it's 1, and t minus t can be any number, so it will be 1. Okay, so all the samples, you say that they perfectly correlate. Okay, and if it's minus, so minus 1, so it depends if it's the next sample or even if this distance is even or odd. So you change sign from sample to sample. Okay, but this is an interesting because we can find these kind of signals in practice that they correlate while the samples are close, but the correlation decays. And suppose that this kind of signal, we add some noise, white Gaussian noise. In the assignment, you can add different types of noise, also whatever you like, okay? But here it's simple. And then we have the measurements of the signal. So the input SNR, you see the input SNR, we can compute it like this. RV, the correlation matrix. The correlation matrix for the noise is sigma v squared multiplied with identity matrix, L by L identity matrix, because it's white noise with the variance sigma v. And the correlation for the desired signal from this model looks like this. So it's alpha, and this is the difference between samples. So along the diagonal, what it will be? Along the diagonal? Along the diagonal, it's 1, right? Because it's alpha to the power of 0. So along the diagonal is 1. So Rx looks like that. It's L by L matrix. Here we have 1s. And here we have alpha, and so on. Here we have alpha squared, and so on, alpha to the third, and so on. So you see, when you have two samples with larger distance, the correlation decays. By the way, there is a name for this kind of matrices. Okay? Okay, so I want to note that here, if we use Rx, if we use this matrix, we assume we know alpha. Actually, is it difficult? Compared to the previous example number 1 that we talked yesterday, over there we assumed it was a cosine signal, and we assumed for the purpose of constructing the matrix Rx, we assumed that we know the amplitude, A, and also the frequency, F0, which is a lot of information. We need to estimate them. Here, we only assume that we know that the correlation. We assume a few things. We know the correlation coefficient, like this. We know alpha. And we also know this model, that the correlation looks like this. Okay? But if you want to estimate Rx from the data, of course, it will contain some errors. Even here, even if you know this, you need to estimate alpha. And if you estimate that from fixed length of measurements, especially noisy measurements, probably you will not have the correct alpha. And then you can ask yourself, okay, what is the effect of incorrect alpha? How does it affect the filter, how does it affect the performance? What is the performance criterion here? We have a few performance criteria. First, we have the mean squared error. And we can have also here the weighted mean squared error. But we can ask ourselves, how does it affect the gain in SNR, the desired signal, the reduction factor, the noise reduction factor, the distortion, all the performance measures that we talked before. We can ask ourselves how inaccurate estimate of alpha, this error in alpha, how does it affect the performance measures that we talked before? This is a good question, and you need to find how does it affect for this different type of signals. Okay, so let's continue. So we can find the trade-off filter from the previous equation, and we can also find mu that satisfies this constraint for different values of aleph. Okay, so first let's assume that we have a certain example. So alpha, suppose that it's 0.8. We have a filter length of L equals to 30, which means that to find an estimate Z, we look for the past 30 samples of the signal, and we can take several values of aleph, how much noise we want to reduce. Okay? So let's see this example. This plot. This is the gain in SNR. These are some performance measures. The gain in SNR, the mean squared error. You see, we check the mean squared error, not the weighted mean squared error. Here is the noise reduction factor, and this is the desired signal reduction factor. So we have 4 lines, 4 plots here, and for different values of aleph. Aleph equals to minus 12 dB, this is the blue, and minus 13 dB, minus 14 dB, the red, and minus 15 dB. So first we see that for different values of aleph, we have the noise reduction factor is constant as a function of input SNR. Of course, because this was our constraint. We chose mu such that the noise reduction factor will be minus aleph. Okay, we wrote it before. Okay, it's here. It's here, this constraint. If we, Jn, this is the mean squared error relative to, based on the noise reduction. So writing this is the same as a constraint that the noise reduction factor will be 1 over aleph, which in dB, it means that the noise reduction factor in dB is minus aleph. That's why we have in this example, we have it here, that the noise reduction factor is constant and equals to minus aleph. So if we increased, or if we want to, aleph becomes lower, so we increase the noise reduction, okay? You see, we have more noise reduction. Aleph lower, it means that we want to reduce more noise. So aleph is lower, see blue, green, red, cyan. So we increase the noise reduction. If we increase the noise reduction, we also get higher output SNR. So the gain in SNR also increases. But we pay for that. What happens to the desired signal reduction factor? Also it increases. Okay, and also the mean squared error increases, which means that if we want to reduce more noise, the distortion will be higher. We'll get higher distortion. We see it from here. The distortion is higher. The mean squared error, You see, when you reduce more noise, you expect, so we have two terms. You reduce more noise. So this part will be smaller. But we get that the mean squared error becomes larger. Okay? So what do you say? What can we say about that? That this becomes smaller, but the total becomes even larger. So this becomes even larger compared to the reduction in the noise. Okay, so the summation of this part, the summation, this is the MSE, the summation of the noise reduction-based MSE and the distortion-based MSE, both of them increase, which means that this increases more than this decreases using the trade-off. On this example, I didn't prove that it's always true, okay? But for this example, you see that even though we increase the noise reduction, we have less noise, the total MSE increases, which means that the distortion increases at a rate higher than the rate of decreasing the noise. It has more effect, okay? Okay, questions on this example? Okay, let's move on. Let's talk about the MVDR filter. Okay, so what is the MVDR filter? We can define it that we want to have distortionless response. So we want this to be 0. With the trade-off filter, no matter what is mu, if you choose mu, you increase it as much as you want. Still, this JD, which means that the signal-based distortion, MSE, it will not go to 0. But suppose that we want this to be 0. So our problem is that we can define the problem or formulate the problem that we want to have 0 distortion. So this will be 0. And then we like to minimize Jn. So it's not spatial case or particular case with a certain mu of the trade-off filter. It's another problem, okay? So this is the MVDR filter. And the question is, before I continue, think about intuitively, the MVDR filter, if we like the distortion to be 0, and then we try to minimize only this part, compared to the trade-off filter, which filter reduces more noise? The trade-off filter or the MVDR? I hear MVDR and trade-off. Okay? Let's think about it. Which one requires that the distortion will be smaller? MVDR or trade-off? MVDR. Okay, so the distortion is smaller. If the distortion is smaller, what does it mean about noise reduction? Less noise reduction, because you have a constraint. You cannot get the more noise reduction that you want, it will cost you that it will increase the distortion. You want to reduce more noise, the distortion will increase. It comes together. So if you require that the distortion will be 0, we have a limit how much noise we can reduce. Okay? And this is a nice thing. So first we have a comparison between Wiener filter, between trade-off filter, and between MVDR, even without deriving the MVDR. Okay? So if we compare we can remove here. Okay. So if we compare the noise reduction factor, Cn for H Wiener compared to noise reduction factor with a trade-off filter compared to noise reduction factor with H MVDR. Okay? Which one will reduce? Which one will be the highest? Highest, it means that we reduce more noise. Which one? Okay, so suppose that we try to suppress noise with a certain signal, and the signal is band limited. Suppose that we sample the signal with 16 kilohertz, and we know that the desired signal is contained in a certain bandwidth, maybe from 1 to 2 kilohertz. What? If the desired signal, exactly what you say. If the desired signal is, we know that it's contained within a certain bandwidth from 1 to 2 kilohertz, we can remove all the low frequencies up to 1 kilohertz and remove all the noise higher than 2 kilohertz, and we get noise reduction without any distortion. This is exactly the NVDR, what it tries to do. It tries to find the signal subspace. The signal subspace in this example is between 1 to 2 kilohertz. And then in this subspace, we don't touch, we don't do anything. We keep it as is. And in the noise subspace, which is up to 1 kilohertz, and from 2 up, higher than 2 kilohertz, we suppress all the noise. Okay. So if we compare it to Wiener filter, the Wiener filter, of course, it will remove all the noise in the noise subspace up to 1 kilohertz, and above 2 kilohertz it will remove, just like the NVDR. But what will it do in the signal subspace from 1 to 2 kilohertz? It will also decrease some noise, but introduce some distortion based on the signal-to-noise ratio. Depends if we have more signal or more noise, because it tries to minimize the mean squared error. The trade-off is very similar to the Wiener filter. It just gives different weight with a parameter mu to the noise, to the signal-to-noise ratio in that signal subspace. Now my question is, do we have to do it in the Fourier transform? Or we do it, what is the signal subspace? Sometimes we call it, instead of signal subspace, signal plus noise subspace. But the noise we assume that is full rank. It's all over. So we say the signal subspace, it contains some noise. And the noise subspace, it's without any signal, desired signal. And then we want to find what is the signal subspace, what is the noise subspace, and then the Wiener will remove, the NVDR will remove only the noise in the noise-only subspace, while the other filters, the Wiener, for example, it will remove the noise in the noise subspace, but also it will distort the signal to achieve more noise reduction. And the trade-off also will trade off how much in the signal subspace we want to remove more noise compared to distortion. This is the intuition behind it. Okay? Any questions? Okay, so we will have 10 minutes break.